Here is our int_stack class from the previous video, and I think it's pretty much identical, although I did change this. On line 23 in the video, I didn't catch myself in time, and I wrote myself a C-style initialization. And so, perfectionist that I am, I had to fix that. Now, you don't need to be nearly as self-conscious for your code because it's perfectly fine to write C-style initializations. But I have to try and be consistent. Who knows who's watching these videos? Probably no one. So what I've changed, though, about this version is instead of just making stacks of ints, I would instead like to be able to make a stack of whatever. A stack of ints, a stack of strings, as long as the element type is cooperative. So, for example, I'm allowed to make copies of it, so it has a copy constructor, then I should be allowed to make a stack of them. The same way that I'm allowed to put just about anything in a vector. And so if I try compiling this, it's going to complain about all sorts of problems. So the biggest one is I still have a class called int_stack. And the compiler, trying to be helpful, suggests that I use some weird standard library feature I've never heard of before. So I guess the first thing I have to do, of course, is define a class called stack to make the compiler shut up. So I wanted my class to be called stack. Okay, there we go. And I don't know, just to give the compiler a hard time, we'll try compiling it again. And now it's really unhappy because it's saying, okay, I get it. I mean, you have a class called stack, but it's not a template. Give me a break, Bill. And the compiler and I have been through a lot together. That's just the way it is these days. We have a certain rapport. And then, of course, it's not letting me work with strings or anything else. So clearly, it's not just defining a class called stack. I actually have to make the class templated. So I'm going to add a template directive. Template type name T. All right, so I've created a placeholder called T. I've attached the template directive to the class stack. Everywhere inside of this class, I can now use T as if it were any other type. And in particular, anywhere I'm working with the element type, I need to write T and not int. So I've got, let's see, T, there we go. The pop function returns an element, that would be T. I don't think I'm using the element type directly anywhere here, but I am using the element type inside of my node class, or my node structure. So let's see, it takes a T, and then the element is stored as type T. And we'll try that out. When you do a substitution like this, it's pretty easy to make some mistakes, so it's better just to let the compiler help you with it. It does look as if it worked. And so we'll just try running it and see what we think. And it runs, and we can see I push 5, 10, and 6, and I pop them, and I should get them in reverse order, and I do. I then make a stack of strings. I push raspberry, pear, pineapple. I pop them, and I get them back in reverse order. Now, as usual, a bit more testing might be a good idea in a context like this, but to keep things moving, I will say executive decision. It does look as if I have templated the class successfully. And we're now about 3 minutes into the video, and I think I've proven my main point, which is that once you have the class working, templates are pretty nice. Once I know what to sub my placeholder in for, so once I knew to convert every reference to int to be T, it was actually pretty easy to turn the class into a template. And that's because I could just copy and paste the stack class to make a stack of strings or floats or whatever. And the template feature allows me the ability to automate this, to make the compiler copy and paste for me. Okay, great. So in general, templating a type really isn't that bad in a lot of cases. Now, of course, there are types that are hard to template, but in general, hopefully this has proven that templates aren't too scary. Now, it's true, though, that templates are the gateway to some serious dark magic. There is some amazing stuff you can do in C++ using templates, but it tends to go far beyond the idea of creating generic types, which is what we're doing here. A lot of languages support generic types, the ability to define a type where a particular, like an element type of a stack, is a placeholder that can be filled in at compile time. Java, for example, supports that as well, with very similar notation. Templates in C++ are far more powerful than that. And that's something we're only going to scratch the surface of in this course. So an example being, in Java, you wouldn't typically have templated functions. There really isn't an analog to templated functions like we saw last week in Java. But there are generic types that use angle brackets to allow you to parameterize a vector or a list or something. I want to talk about a couple of other things you might see while creating a templated version of a class. So in this version, and I think this is a good practice in general, we decided that because our stack uses a linked list as its underlying storage, we should define the machinery for that linked list in the class, because it shouldn't be anybody's business outside of our class what we're doing. So we define the whole list. The node type is private to the class. The whole list is entirely encapsulated. But there are cases where you might want the node class to exist outside of the stack class. One example is maybe you have a lot of different data structures all using nodes, all representing their contents with a list, and therefore having the node type exist outside of the class might be a good idea. We need to talk about how that works with templates. It does result in a little bit more of a notational mess. So here I've got a stack class where I'm still templating the stack class with a template parameter t. I push elements of type t, I pop elements of type t. But in this version, I have not put the node class itself in my stack class. Instead, the node class is located elsewhere. And that means that I want to be able to create nodes of any element type. And because the node class is not inside of the shelter of the stack class, that means the node class needs to be templated itself. I need to be able to make nodes of any element type. Here I've defined a template where the parameter is called element type. And inside the node class, I have to define my own node pointer type, which is a shared pointer to a node of this element type. Obviously, I don't want to mix together nodes of different element types. If I'm inside a list of ints, I want to stay inside a list of ints. So in the context of the node type, a node pointer is a pointer to another node of the same type, including the same element type. And then otherwise inside the class, I have the same machinery that I had before. Similarly, down in my stack type, when I define node pointer for inside of the stack, I have to have it be a pointer to node of t, because t is the template parameter for the stack. And because node has its very own template directive, if I'm using a node inside of the stack, I have to explain what I want the template parameter for node to be. I want to pass through my parameter t. Everything else works sort of as expected. Although when I use make shared, I again am making a node of t, not just a node. Contrast that to my other stack class where I just say type node because it's understood that the node uses element type t because it's subject to the same template directive as the rest of the stack class. So it is a little bit more messy to have the node type be separate from the stack type. And that's one of the reasons I encourage you not to do that. But you might see code out there in the world that does this, and you should understand that although it's more messy, it's not really that different. It just requires more notation to indicate, to sort of line up the template parameter for stack with a template parameter for node. And I can run this just to make that clear. I'll scroll down to main to show that it's the same testing code as before. There we go, and it does compile, and I can run it, and it does give the correct output. And I have one more question. This is a nasty one. So what if I wanted to print out these stacks? And I really shouldn't do this because the whole point of the stack is that I can only see the top element. But while we're on the subject of templated classes, let's talk about it. Suppose I wanted to write a print operator, so the stream insertion operator that prints an entire stack. And I guess we'll print the top of the stack first and the bottom of the stack last. How would I do that? Well, okay, let's mock it up here. So I know already that I'm going to write my stream insertion operator. There it is. It's going to be operator this. And then I think, okay, so I'm going to take the stream as the left-hand argument. And then wait, what do I take as the right-hand argument? I guess I want to be able to print out stacks of anything. So I take a stack of t. But wait a minute, am I allowed to use type t for this operator? And the answer is no, because this operator is not subject to a template directive. So if I want this operator to work on stacks of anything, I need to define a placeholder for this operator. And you're allowed to attach a template directive to a function or a class or an operator or a variety of other exotic things. Anywhere I want to use a placeholder type, I need to be underneath the shelter of a template directive. Otherwise, the compiler will complain. In fact, let's see what happens if I try compiling this. It has a few complaints, but the first one, the biggest one, ought to be that I don't know what t is. You're using type t. What is t? And so what I have to do is tell the compiler, yeah, t is a type that I haven't produced yet. So it's a placeholder. Just give me a minute. And then when I use the operator, you can figure out what I mean by t. So here, when I try and push the stack S1 is a stack of ints. So when I'm taking a stack of t, the compiler should be able to deduce that I want to use int as t. But until then, when I'm defining the operator, I need to say, look, this is still a template. I still have unknown information. There's still a placeholder. But it sort of gets worse, because think about it. Okay, normally when I write operators that operate on a class, I have the option of putting the operator inside the class. But I can't do that here. I can't put this operator inside the stack class because stack isn't the left-hand operand. If I want to iterate over the stack, what do I do? Well, I guess maybe you remember how to write lists that iterate over how to write loops that iterate over linked lists. I would do something like this. Start at the head of the list. Wait a minute. The head of the list is private. And I don't want to make the head of the list public. I want to make sure that nobody in the outside world can see the head of my list, except maybe this operator. And we can see things are just piling up here. Not only do I have to have a template directive, I have to get into the class and use its private data. Okay, well, fortunately for us, we don't need to go through this agonizing exercise in this course. This is a little bit too crunchy for CSC 116. But since I think it's a useful question, and I do think it's worth at least seeing the solution, let's go over the solution. So here in main, I am able to print out both of my stacks, and I'll prove that by compiling and running the code. There we go. It does compile, and I can run it, and we can see it does print out both stacks. Of course, when it prints them down here, they're empty. Let's see what happens if I don't pop the stack. So I'm going to, because when I pop each stack, it is removing all the elements. Suppose I just push elements into the stack, and then I try and print both stacks. Okay, I deliberately showed off the empty thing that was printed because I didn't want you to think from the fact that I'd commented out the code that I was somehow screwing around with the example. Okay, so I push elements and we can see here the print operator apparently works. Let's just take in what it has to look like. It is ugly. So first, the print operator, like before, needs to have a template directive attached so that it can work with stacks of anything, not just stacks of int. But then when I iterate over the stack, and we'll talk more about iterating over linked lists in I guess, one of the next two videos, when I iterate over the stack, I have to work with a couple of things that are private. So the head pointer in the stack is private. What isn't shown here that's actually a little bit more scary is that the node type is private. So if I want to work with pointers to node, which are being concealed by this auto, if I want to work with pointers to node, I need to know about the node type. And if I'm outside the class and the node type is private, that means I need private access. So not only does this operator have to have a template directive attached to it, the operator has to be a friend of the class because the operator isn't allowed to live inside the class, which is the normal way you give private member access to an operator. I can't do that because the operator doesn't take as its left operand a stack. So if I want the operator to have private member access, the only option is a friend directive. Okay, so how do I make a friend directive? Well, I take the signature of the operator and I put the word friend in front of it. But it gets worse because the operator now, the signature of the operator involves a template parameter. And therefore, I have to attach a template directive to the operator when it's a friend directive. Yuck! So that's one reason we don't have to worry about this in CSC 116. I wanted to show off, though, that templates are great, and operators are great, and friend directives in the right context can be great. We can see, though, that because the language provides us so many tools, and there are so many rules that can get in each other's way, when we sometimes have to write perfect abstractions, we end up with really ugly results. And that's a consequence of a language like C++. We get all of this power, and sometimes wielding the power is a bit cumbersome. And you will notice if you ever take a look at the source code for std vector or std list, it is full of nasty looking notation like this. Because sometimes you need a lot of different features at once to produce that perfect crisp abstraction to the outside world. And I would say we've succeeded. Although that notation was ugly, in main, it looks pretty beautiful. I can make stacks of anything. I can push stuff into them. I can pop stuff. I can then push them into this stream using a stream insertion operator, where the stream insertion operator is templated and it's somebody's friend, but I don't care. I just use the operator in main. So although creating the abstraction is ugly, I can still put it all under the hood. From the point of view of somebody using the stack, I still get a great abstraction. However, all we care about for exams in 116 is the ability to make templated types, a really big deal, and some understanding of the fact that when I have a templated type that is itself using another templated type, there is a bit of cumbersome notation associated with that, because the node type needs its own template directive, which means when I use the node, I have to use angle brackets to indicate what its parameter type is.